Welcome to this video, which is for A-level maths students where we take a closer look at rationalising the denominator. If you need a reminder of what's meant by rational and irrational number, then make sure to watch the video on my channel, to which I'll put a link in the description which goes through all that kind of stuff. But let's jump straight in. So rationalising denominators of expressions of the form p over b root c, where b is an integer and c is a non-square integer. P can be anything, but will often, but not always, be an integer. This is easy. Simply multiply the numerator and denominator by the square root of c to give p over b root c is equal to p root c over bc. And since b and c are integers, then so is their product bc, and so it's rational. For example, 2 over 5 root 11, this is equal to 2 root 11 over 55. Rationalising denominators of expressions of the form p over a plus b root c, where a and b will be assumed to be integers and c is a non-square integer. P can be anything again, but will often, but not always, be an integer. So here simply multiply the numerator and denominator by a minus b root c to give p over a plus b root c is equal to p times a minus b root c over a squared minus b squared c. And since a, b and c are integers, then so is a squared minus b squared c, and so the denominator is rational again. For example, if we consider the expression 3 over 5 minus 2 root 5, this is equal to 3 times 5 plus 2 root 5 over 5. Of course, it may be necessary to cancel any common factors in the numerator and denominator once the denominator has been rationalised, and it's up to you to make sure that you check for any further simplifications that need to be made. So next we're going to look at rationalising denominators of expressions of the form p over a root c plus b root d, where a, b are integers, c and d are non-square integers, and p can be anything. So this is very similar to the previous case. Simply multiply the numerator and denominator by a root c minus b root d to give p over a root c plus b root d is equal to p times a root c minus b root d over a squared c minus b squared d, where the denominator is an integer and so is rational. For example, 2 over 3 root 5 minus 2 root 2 is equal to 2 times 3 root 5 plus 2 root 2 divided by 37. I've maybe been a bit fussier than I really needed to be by separating the second and third cases, as I have done, because arguably they can both be considered as expressions with denominators of the form q plus r, say, where at least one of q and r is of the form a root b, where a and b are integers and b is not a square number. So if we have an expression of the form p over q plus r, with q and r as described, then multiply numerator and denominator by q minus r to give p over q plus r equals p times q minus r over q squared minus r squared. Even the first case that I gave can be considered as having a denominator of the form q plus r, but just where r is equal to 0. And it really doesn't matter how you think about it. What matters is that you're able to rationalise denominators of expressions when you need to, regardless of the form that they appear to have. And I'm not going to suggest that you will not come across denominators of forms other than these three that I've mentioned here. Admittedly, at A level, rationalising the denominator will often be limited to denominators of the form a plus b root c, or at a stretch, a root c plus b root d. However, if you come across a denominator that is of a different form, then you may have to do some work to bring the denominator into the right sort of form before rationalising, or you may have to adapt what you know about rationalising the denominator to suit this new situation. This is, after all, called problem solving. And it may be that you're given some guidance, or you may not be given any guidance. The point is that you have to be prepared to deal with unexpected situations. So let's have a look at some problems now. There's no shortage of routine examples in A-level textbooks of how to rationalise denominators for expressions such as 2 over root 5 or 3 over 7 plus root 7. So rather than waste time on stuff that you already have available to you in abundance, let's have a look at rationalising the denominator from a different angle by considering some less routine problems. Rationalise the denominator of 1 over root 3 plus root 2 all squared. So one way to rationalise the denominator here is to expand out the denominator to get 1 over 5 plus 2 root 6, and then rationalise the denominator 5 plus 2 root 6 by multiplying numerator and denominator by 5 minus 2 root 6 to give 5 minus 2 root 6 over 25 minus 24, and finally 5 minus 2 root 6. But I prefer the following approach. Multiply numerator and denominator by root 3 minus root 2 all squared to give root 3 minus root 2 squared over root 3 plus root 2 times root 3 minus root 2 all squared. The denominator can be seen to be just equal to 1, which gives root 3 minus root 2 all squared over 3 minus 2 squared, which of course is just equal to root 3 minus root 2 all squared. Rationalise the denominator of 1 over 2 over root 5 minus 3 over root 15. So one of the first things that I notice here is that the square root of 15 is equal to the square root of 3 times the square root of 5. And so I can rewrite this as 1 over 2 root 3 over root 15 minus 3 over root 15. And multiplying numerator and denominator by root 15 gives square root of 15 over 2 root 3 minus 3. And now multiply numerator and denominator by 2 root 3 plus 3 to give root 15 over 2 root 3 minus 3 times 2 root 3 plus 3 over 2 root 3 plus 3, which is equal to root 15 times 2 root 3 plus 3 over 12 minus 9, which is equal to root 15 times 2 root 3 plus 3 over 3, which of course has a rational denominator. But we're not quite done yet because the numerator, when expanded, gives 2 root 45 plus 3 root 15, and which after simplifying the surds, and yes, you do need to do this, is equal to 6 root 5 plus 3 root 15. And so square root of 15 times 2 root 3 plus 3 over 3 is equal to 6 root 5 plus 3 root 15 over 3, which in turn is equal to 2 root 5 plus root 15, which is fully simplified. Express 1 over 1 plus root 2 plus root 3 with a rational denominator. So I've included this because it's something that shows how sometimes you just have to go with the flow when solving a problem. I just wrote this expression down and decided to rationalise the denominator of it just to see where things went. I initially had no idea about how the solution of this would ultimately go, so I'm going to present the first solution I found to this problem, how it came to me. It's not particularly difficult, but it really just depends on you being willing to generate ideas and just follow through with those ideas. So my initial idea was to try to adapt the approach taken at A level for rationalising denominators and to do something similar, with big inverted commas around the word similar, because that could mean all sorts of things. However, doing something similar here to me meant multiplying the numerator and denominator by 1 minus root 2 minus root 3. That is, just changing some of the signs from positive to negative. And this gives 1 over 1 plus root 2 plus root 3 times 1 minus root 2 minus root 3 over 1 minus root 2 minus root 3, which is equal to 1 minus root 2 minus root 3 over 1 plus root 2 plus root 3 times 1 minus root 2 minus root 3, which is equal to root 3 plus root 2 minus 1 over 4 plus 2 root 6. And so now the solution proceeds along the same sort of line of approach that you would typically use to rationalise a denominator of the form a plus b root c. So we get root 3 plus root 2 minus 1 over 4 plus 2 root 6 multiplied by 4 minus 2 root 6 over 4 minus 2 root 6, which simplifies to give 2 plus root 2 minus root 6 over 4. And I'm sure that there'll be much more efficient solutions to this problem, and I invite you to have a go at finding a better solution. This was just the solution that came to me from a cold start. The point being that usually whatever you have in front of you, at A level at least, will probably be sufficiently like something that you're already familiar with so that you can at least have a go. You have to be prepared to try and fail before you succeed. Now, from this, I can see that I could have solved the problem like this. I could have just multiplied the numerator and denominator of the original expression by 2 plus root 2 minus root 6 to give 1 over 1 plus root 2 plus root 3 times 2 plus root 2 minus root 6 over 2 plus root 2 minus root 6, which is equal to 2 plus root 2 minus root 6 over 1 plus root 2 plus root 3 times 2 plus root 2 minus root 6, which is equal to 2 plus root 2 minus root 6 over 4. But I wouldn't know to do this initially just from looking at the denominator. However, there does appear to be a general formula that can be used to rationalise denominators of the form a plus b root 2 plus c root 3. In other words, there are expressions in terms of a, b and c for the numbers p, q, r and s in the expression p plus q root 2 plus r root 3 plus s root 6, so that a plus b root 2 plus root 3 times p plus q root 2 plus r root 3 plus s root 6 is equal to a rational number. But I won't include the formulae here. Again, I invite you to have a go at finding these formulae because these kinds of things will really help you to appreciate the intricacies of mathematics more. You may be asking, why do I include root 6 in the expression? And the answer to that is because the calculation that I did to the previous example shows me that I need to include a root 6. Notice that I didn't include root 6 originally because I didn't know that it would be needed, though I might have had an idea that it would be needed somewhere during my solution. It's not difficult in principle to derive these general formulae that I'm talking about, and in fact, it's very easy to figure out what to do to obtain such expressions from what I've done in this example, but it will give you some good practice with algebraic manipulation. It's not always necessary to rationalise a denominator. Sometimes in doing so, you may disrupt a certain pattern and produce an expression that doesn't have the same aesthetic appeal as the one that you started with. For example, 2 plus root 3 over 2 minus root 3. Whether or not you rationalise the denominator of this expression or any other is up to you. Of course, if you're specifically told to rationalise the denominator, then do so. Rationalise when you see that it really needs doing, but then there is this grey area where you need to use your own judgment. Sometimes rationalising a denominator can make spotting patterns much more difficult and therefore disrupt your solution. So it's not a good idea to just indiscriminately rationalise. Nevertheless, you still need to be able to do it. There's nothing wrong with irrational denominators, and it's not always easy or even possible to rationalise a denominator. Sometimes some irrational denominators are best left alone. But as with many techniques that you learn about at A level for simplifying algebraic expressions, you're given these techniques because they're useful. But for them to be useful, you have to be prepared to use them, and you really need to develop facility with them. If you have to consciously think about all of these basic techniques, or maybe you only tend to apply them when you're told to do so, then you're going to create a lot of unnecessary work for yourself. Once you've done a few dozen isolated examples of rationalising denominators at A level, then you should be looking to get any further practice with rationalising denominators through using the technique as part of your solution to other more complicated problems, or at least looking for opportunities to rationalise the denominator for expressions with more complicated denominators than, say, a plus b root c. And after a few weeks, it should really only take a few seconds to rationalise a denominator, and the process should be almost automatic, at least for simple cases. If after a few weeks it's still taking considerable time to rationalise a simple denominator, then it's taking too long and you need to address that problem as soon as possible. If you're unsure about whether or not to rationalise a denominator, then just rationalise it and see what the expression looks like afterwards. Compare the result with what you started with, and this may give you the clue that you need about whether or not you need to do it. Sometimes you have to do things that once you've done them, you realise you didn't need to do them after all. At first, this may happen quite frequently, but over time, you'll start to get better and better at predicting what things are going to look like in your head without actually having to go to the trouble of writing it out. Don't be afraid to do something because you may not ultimately need to do it. It's not a mistake to do this, and it's through just going ahead and doing things and then possibly having to backtrack where you'll really start to develop a real sense of what is and is not necessary as part of your solution. So in this part of the video now, the extra stuff section, we're going to take a look at rationalising the denominator in a bit more detail. So first I'll take a quick look at why rationalising the denominator works, at least for typical routine A-level rationalisations, and then I'll take a look at some more complicated examples. My aim is not to give a complete and comprehensive treatment of rationalising the denominator, but simply to draw your attention to the possibilities that may lay ahead if you decide to continue your mathematics studies beyond A-level. Most, if not all, of this part of the video is not A-level examinable, which is not to say that you derive no benefit from knowing something about this stuff, but simply that I wouldn't expect it to appear on an A-level maths exam, though something similar could possibly appear on, say, a STEP exam. Anyway, let's have a look. If the denominator is of the form a plus b root c, where a, b and c are integers with c not a square number, and so therefore the square root of c will be irrational, then typically to rationalise this denominator, we choose to multiply the numerator and denominator by a minus b root c. And the reason for this is demonstrated in the following argument. 1 over a plus b root c is equal to 1 over a plus b root c times a minus b root c over a minus b root c, which is equal to a minus b root c over a plus b root c times a minus b root c, and then expanding out the brackets in the denominator gives that this is equal to a minus b root c over a squared minus b squared c. And since a, b and c are integers, then the denominator a squared minus b squared c must also be an integer and hence rational. And that's it. And of course, the case of denominators of the form a root c plus b root d is very similar, and I leave it for you to have a go at yourself. And of course, it's clear that the motivation behind this technique is to take advantage of the difference of two squares type of expression and its factorization, since the difference of two squares expression has no cross terms, which here would correspond to the irrational numbers that we want to eliminate. Okay, so here we'll take a look at how rationalising the denominator might look for more complicated denominators, and where the process is less routine. And that's not to suggest that there isn't a general approach that can be applied, at least in theory, but depending on the level of generality that we're considering, the theoretical general approach may turn out to be practically very limited. The solutions to the following problems are just the solutions that first occurred to me and therefore will not necessarily be the most efficient solutions, and they certainly don't represent the way of going about these problems. A problem can usually be solved in many different ways, and I encourage you to find alternative and possibly better solutions for yourself. So let's have a look at rationalising the denominator of 1 over 1 plus 2 times the cube root of 2 plus 3 times the cube root of 4. And here it's worth noting that the cube root of 4 is equal to the cube root of 2 squared, and that the cube root of 2 cubed is equal to 2. So just to simplify things a little bit notationally, we're going to denote the cube root of 2 by x, then 1 over 1 plus 2 times the cube root of 2 plus 3 times the cube root of 4 becomes 1 over 1 plus 2x plus 3x squared. And one way to approach rationalising this denominator is to ask for another expression, a plus bx plus cx squared, such that 1 plus 2x plus 3x squared times a plus bx plus cx squared is equal to a rational number. Now there's no guarantee that such an expression will exist, but we can always try to find out. And this is similar to what we do with denominators of the form a plus b root c, where we look for an expression p plus q root c such that a plus b root c times p plus q root c is equal to a rational number. And it turns out that in the case of a plus b root c, that one possible expression is given by a minus b root c. However, we have that 1 plus 2x plus 3x squared times a plus bx plus cx squared is equal to the expression as shown on the screen. And remember that x cubed is equal to 2. And so, if this is to be a rational number, we require that 2a plus b plus 6c is equal to 0, and 3a plus 2b plus c is equal to 0. And now, setting a equal to 11, because having done the calculation which follows, I know that this simplifies the calculation, then we obtain the corresponding values of b and c, which are b equals minus 16, and c equals minus 1. And so we have that 1 plus 2x plus 3x squared times 11 minus 16x minus x squared is equal to a rational number, which in this case is minus 89. And so 1 over 1 plus 2x plus 3x squared is equal to x squared plus 16x minus 11 over 89. Or in other words, 1 over 1 plus 2 times the cube root of 2 plus 3 times the cube root of 4 is equal to the cube root of 4 plus 16 times the cube root of 2 minus 11 over 89. So now let's try rationalising the denominator of 1 over 1 plus the cube root of 2 plus the cube root of 4. And using a similar method, therefore, we try to find a plus bx plus cx squared such that 1 plus x squared times a plus bx plus cx squared is equal to a rational number. And we get 1 plus x squared times a plus bx plus cx squared is equal to the expression as shown on the screen. And so we need a plus b plus 2c equal to 0, and a plus b plus c also equal to 0. So here c must be equal to 0, which gives a plus b equals 0, and therefore choosing a equals 1, then b equals minus 1. And so 1 plus x squared times 1 minus x is equal to minus 1, giving 1 over 1 plus x squared is equal to x minus 1, or 1 over 1 plus the cube root of 2 plus the cube root of 4 is equal to the cube root of 2 minus 1. Alternatively, if we let z equal to 1 plus x squared, then z squared is equal to 5 plus 4x plus 3x squared, and z cubed is equal to 19 plus 15x plus 12x squared. And then it can be shown that 3z plus 3z squared minus z cubed is equal to minus 1, or in other words, z cubed minus 3z squared minus 3z is equal to 1. And so dividing through by z, we get that 1 over z is equal to z squared minus 3z minus 3, and therefore 1 over 1 plus x squared is equal to x minus 1. Or in other words, 1 over 1 plus the cube root of 2 plus the cube root of 4 is equal to the cube root of 2 minus 1, which of course has a rational denominator. This second alternative solution is using the idea of a minimal polynomial of an algebraic irrational. Rationalising the denominator can become quite difficult and laborious beyond a certain point. Even fairly simple denominators which involve cube roots can get quite involved, and the process can be less systematic than the kinds of things that you might encounter at A level. If the irrational that appears in the denominator is algebraic, then at least in theory, the denominator can be rationalised. If the denominator is a transcendental irrational, then there's probably not all that much that you can do, and in this case it's probably best to just leave it alone. At A level, rationalising the denominator to me represents a technique which can be used to make your life easier when it comes to solving more complex problems. In other words, at A level, rationalising the denominator is more of a means to an end rather than an end in itself. However, rationalising the denominator can be made more, let's say, interesting by varying the form of the denominator that you wish to rationalise. But even then, once we've considered several different forms of denominator and possibly found general methods by which these types of denominator can be rationalised, we may, as mathematicians, finally be led to the problem of finding a general way of rationalising any form of denominator, or at least those which contain algebraic irrationals. And it may seem odd, but although we may search for a general method by means of which any denominator can be rationalised, this doesn't necessarily mean that we're interested purely in rationalising denominators. There's often an ulterior motive. That ulterior motive may be to find out what kind of theory can be derived from attempting to solve such a problem. The problem of rationalising the denominator may just be something that's used as a tool to generate theory in a new direction. Okay, so I said I wasn't going to include these formulae in the video, but since you've watched to this point, here you go. So here I'll give the general formulae that can be derived for rationalising the denominator of expressions of the form 1 over a plus b root 2 plus c root 3. So if we assume that there is an expression of the form p plus q root 2 plus r root 3 plus s root 6, such that a plus b root 2 plus c root 3 times p plus q root 2 plus r root 3 plus s root 6 is equal to a rational number, then it can be shown that possible expressions for p, q, r and s in terms of a, b and c are, as shown on the screen now, p equals a times a squared minus 2b squared minus 3c squared, q equals minus b times a squared minus 2b squared plus 3c squared, r is equal to minus c times a squared plus 2b squared minus 3c squared, and s is equal to 2abc. Actually, to derive these expressions, I didn't initially assume an expression of the form p plus q root 2 plus r root 3 plus s root 6. I took what seems like a longer approach, similar to the approach that I took in the example earlier in the video, the third example, but which turned out to be less messy algebraically. In other words, I calculated a plus b root 2 plus c root 3 times a minus b root 2 minus c root 3, which turns out to be a squared minus 2b squared minus 3c squared minus 2bc root 6. And so I know that a squared minus 2b squared minus 3c squared minus 2bc root 6 times a squared minus 2b squared minus 3c squared plus 2bc root 6 will be rational. And so the expression p plus q root 2 plus r root 3 plus s root 6 that I need will be equal to a minus b root 2 minus c root 3 times a squared minus 2b squared minus 3c squared plus 2bc root 6. And I'll leave you to figure out all of the details for yourselves. Have fun. So there we have it, rationalising the denominator in a nutshell, which brings us to the end of this video. Thank you for watching right to the end, and I hope that you found the video useful and interesting. Please remember to subscribe to this channel and click the like button to show your support. I'll be continuing to upload videos to this channel as often as I'm able to do so over the coming weeks and months. But in the meantime, if there is anything that you'd like to ask about what I've covered in this video, or about mathematics in general, then please feel free to get in touch. Valete omnes.